Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to talk about moisture and shrinkage in wood and how water and wood interact and how that affects the wood. So wood and water have a dynamic relationship where the water will affect the wood not only in size and shape, but also in strength and behavior. And the strength parts we're going to cover kind of later. But today we're going to cover about how it affects the size and dimensions and what kind of consequences that can have. So when a tree is growing, the wood in the tree has a very high moisture content. In the sapwood, which is the wood towards the outside, the outer rings, this is the part of the wood that is involved a lot in transportation of water throughout the tree. And so the moisture content is very high. You can see 150%. There's tons of water in there. Okay. In the heartwood, it is moist just as a function of being within that wood and through diffusion from other parts of the tree. Now, as soon as we cut down that tree and there's no more active water flow through the tree, that wood is going to start to dry out and lose moisture. Okay. Down here in the middle, you can see the same kind of figure that we looked at when we were talking about the structure of wood. These are all of the wood cells. The thick parts are the cell walls, and inside the cell walls there's a space, and that's an open space where water can be. Now, inside the tree, it can accept water in two different ways. The first way that it's going to accept water is as bound water, which is shown here, which means the water that goes into the wood goes directly into the cell wall and gets bound into that cell wall. It gets joined to the cellulose that's in the wall through hydrogen bonding, and those walls soak up that wood like a sponge. Those walls can only accept so much water before they become completely saturated. Once any more water goes into the wood beyond that, then instead of that water going into the cell walls as bound water, it goes inside the holes inside the cells as free water. So those are the two different ways. One is the free water, that's just water sitting inside the holes in the cells, and the other is bound water, which is water that's actually bound within the cell wall soaking it up like a sponge. Now, in the process of soaking up water like a sponge, the dimensions and size of that cell wall are going to change. So if we start as dry, which is on the right, and the cell wall is dry, it's going to have a certain size. Now, when water is added to that, the cell wall is going to expand like a sponge. So it basically gets bigger. All the wall thickness is going to get bigger. The total dimensions of the cell are going to get bigger. And that happens for the entire time that you're adding water that gets bound into the cell walls. So any bound water that we add or remove from the cell walls is going to change the dimensions of the cell walls. So we can add water, add water, add water. Cell wall gets bigger and bigger and bigger. At some point, it's going to reach a place where it can't actually physically soak up water anymore. And that point is called the fiber saturation point. It's the point at which the fibers are saturated with water. Beyond the fiber saturation point, if we add any more water, it's not going to go into the cell walls. It's going to go inside the cells as free water, which you can see here. Now, that free water being inside the cells does not change the size of the cells. So if we're looking at a piece of wood and we start dry, and we add water to it, it will expand, okay, up to the point that we've added enough water that it's going to saturate the cell walls. If we add any more water to it past this point, then the dimensions are not going to change anymore. So obviously the fiber saturation point is an important point that we need to consider if we are trying to figure out how much the wood is going to shrink or swell. If we go the other direction, let's say if we cut down a tree and the tree is all the tree's fibers are saturated and there's free water within the cells, and we start to dry it out, the first water that's going to go away is the free water until the point that it reaches the fiber saturation point. During that change, the dimensions of the tree have not changed at all. And then if we dry it out further past the fiber saturation point, that's when we're going to get this shrinkage. And that shrinkage happens predominantly in the cell wall expansion and contraction in cross section, and not very much in the longitudinal direction of the cell. So in the longitudinal direction of the cell, this up and down distance, if we're looking at this piece, or this distance, which is also called the grain direction of the piece of wood, which is the direction that the grains, that the fibers are oriented, then we don't have a lot of shrinkage in that dimension. There's some, but an order of magnitude smaller than what happens in the other two directions. Okay, if we look a bit closer, and we're talking about green lumber to dry lumber, there's basically two effects that change the size of a piece of wood between when it's cut down and initially cut into shapes like this, and the time that you use it as lumber. So it starts off as green right when let's say I cut down the tree, I bring it to the sawmill, and at the sawmill, we're going to cut it into boards or planks or lumber sizes. Between the time that that process is done and you buy it at the store, or you get it from the lumber yard, or it's used in construction, the size of that piece of wood is definitely going to shrink. So it's going to start past fiber saturation, and then once it gets to moisture saturation that is reasonable for use in construction, down below, say, 18%, something like that, then it's going to have shrunk in size, and then we have our dry lumber size. Now, on top of that size change, there is also a mechanical size change happening, because they're going to plane off the edges of the pieces of lumber so that the sides are not so rough. So that's also going to change the size of the cross section. So that's why if we cut a piece of lumber at the sawmill 2 by 4, 2 inches by 4 inches, when we get it at the store, it's not 2 inches by 4 inches anymore, because A, it's shrunk from a green condition, and B, it has been planed off to become smooth. So that's why a 2 by 4 is actually more like 1.5 by 3.5. To calculate moisture content in wood, the equation is very simple. These are weights, where we have basically the weight of the water in the wood divided by the oven dry weight of the wood. Okay, so it's basically like how much weight of water is in that wood versus how much does the wood weigh itself. So 100% moisture content means there's as much weight of water as there is of wood. Now, if I want to find out how much water was in the wood, what I have to do is I have to weigh the wet piece of wood and then dry it out, weigh the dry piece of wood, and then I can find the difference between those two is how much weight of that was in water, right? So if I start with a wet piece and I remove all the water and I measure a dry piece, the difference is obviously how much water was in there. So that's one way that I could calculate that. Now in practice, we can use electrical resistance measurements to determine moisture content. We don't have to go through this process of physically drying out the piece of wood, and that's something that I will show in the live session. Okay, as we mentioned at the beginning, wood is in a dynamic relationship with the water in its environment. So when I cut down a tree and it starts out green, it dries out. Well, why does it dry out when I cut it down? That's because in the air, there's less water than there was in the tree, right? Because the tree is constantly putting new water in, coming from the roots, coming from rain, et cetera, et cetera. But if I just leave it out in the air has some water in it, but not as much as was actually in the tree due to the active processes of the tree. So that means it's going to dry out. Any water that's in there is going to off gas until the point that the water going out is exactly equal to the water coming in, right? Because there's water in the air. That water will also go into things that are dry, right? That's the reason why, crackers go stale if you leave them out, right? You have a dry cracker, you leave it out. It takes in water from the environment until it gets in equilibrium, and then you have kind of like a soggy, stale cracker. So this process works in both directions, and it works until such a point as the wood is in exact equilibrium with its environment. But that process does not happen instantaneously. It takes quite a bit of time. So if you want to dry out a piece of wood, you have to put it at the equilibrium. You have to put it inside a relative humidity that you want for some certain amount of time. And the larger the piece of wood, the longer that's going to take, because this is a diffusion process of getting water out of the wood. So here you can see the effect of equilibrium moisture content in wood as a function of temperature and as a function of relative humidity. So if I start with a dry piece of wood that I put into the roof of a pool or something like that, so that it's inside a space where there's very high relative humidity, then the equilibrium moisture content is going to increase over some period of time. Let's say it's 21 degrees and I start at 0 and I put it in a kind of high relative humidity environment, then the equilibrium moisture content is going to increase until up to a maximum of about 32%, which is beyond the fiber saturation point. Okay, if it's hot, then we will have less moisture in the wood. Okay, so I alluded to earlier that shrinkage is different in different directions inside the wood. So we're going to look at each of these, and these are the three directions of wood. The first one is tangential direction. So tangential direction is basically the direction around the circle of the ring. Okay, so around the circle of the ring, that's the tangential direction of the wood. So if I take a piece of wood from high moisture content above the fiber saturation point, which is around 28%, okay, and I dry it out, then basically my wood is going to shrink, and it's going to steadily shrink the more I dry it out. And so for example, if I dry it from the fiber saturation point down to 10% moisture content, then I'm going to have about 4% shrinkage, which, as you can imagine, is a lot. So if I have something that's 100 millimeters long, after that, I'm going to lose 4 millimeters, right? So I'm going to end up at 96 millimeters long. Okay, and the calculation is not much more difficult than that, right? So that means that the tangent, that circle, is going to shrink. Okay, if I talk about the radial direction of wood, okay, so this is the direction from the pith out to the circumference, okay, shrinkage in that direction is a little bit different. It's a little bit less. Okay, so it's going to shrink less radially than it will circumferentially. Okay, so circumferential shrinkage is like making the circle smaller. Radial shrinkage is basically shrinking the radius of the circle, and it would shrink in all directions. Okay, so it's a little bit less than the tangential shrinkage. Okay, now if we talk about longitudinal shrinkage, which is shrinkage along the length, so if I have a 2x4, the long dimension of the 2x4 is the grain direction. Okay, so that length of the 2x4 will shrink much less than the cross-sectional dimensions of the 2x4 will shrink. Okay, so longitudinal shrinkage in wood, as I mentioned before, is generally much less than radial or tangential. Now in practice, when we're looking at wood, we don't really know which direction is which in a specific piece of lumber, but you can see that radial and circumferential shrinkage, or tangential shrinkage, sorry, are very similar. So we just tend to treat those two as the same, and then the longitudinal we give a very low value because it's the one that's different, significantly different. So when we have a piece of wood, we don't really care which direction is tangential and which direction is radial. We treat them the same in design. Okay, so this is some examples. This is another nice picture that shows kind of what it looks like if I were to take a structural piece of lumber out of a large piece of wood, how much it's going to shrink. Okay, you can see in the tangential direction, which is in this direction, it shrinks somewhere between 6 to 13% if we go from fiber saturation all the way down to 0 moisture, and 2 to 8% in the radial direction here. Okay, and then in the longitudinal direction, you can see we're a whole order of magnitude smaller, so 0.1 to 0.2%, which is very small. And here on the right, you can see shrinkage values for different species of wood. So obviously, as we talked about in another video, since wood is a natural material, we have all different types of species that we deal with. And of course, none of them are the same, and they're all going to be a little bit different. But you can see in general, tangential is always greater than radial, and both of those are a lot greater than longitudinal. Okay, so some other negative effects of shrinkage besides the point that the piece of wood is going to get smaller in cross-section is that depending on where we cut the piece of wood out of a tree, I could get warping of my piece of wood. So if you see here, for example, on the top left, I don't have in my piece of wood one direction that's tangential and one direction that's radial, because my piece of wood is a rectangle, but the lines of the tangent are curves. So that means that I'm going to have a different direction shrinkage out here than I'm going to have over here, which means that I could get warping in my piece of wood, which might be a negative for me if I'm trying to build a structure that's straight. Okay, so we see other ways that we can get warping. So obviously cutting a piece of wood like this is much better for warping than cutting a piece of wood like this. Okay, so one way that we can reduce this amount of warping is by controlled drying. So drying basically in a kiln or in a nice controlled way where we have covered the wood so that we're not letting it just dry all willy-nilly, we can reduce the amount of warp by kind of controlling the rate of drying. This is what it looks like to put some big pieces of wood or a big platens of wood into a kiln for drying. And this is what you get when you have some lumber from Home Depot. And if you've ever gone and got lumber from Home Depot or seen somebody getting lumber from there or wherever else, Rona or what have you, and you probably see people picking up the pieces of wood and then laying them down straight and seeing which way they warp, because in general, all the pieces of lumber that you get at a place like that usually are quite warped, and that has to depend on drying, but it also depends on the grade of the wood. So depending on what grade of wood you have, it might be more or less prone to this kind of warping. Okay, as I mentioned earlier, the specific gravity, which is a measure of density of wood, the substance itself. Okay, so I'm talking about kind of the cell wall substance with the lignin and the cellulose, is heavier than water. And so wood substance itself is quite dense. But as we know, a piece of wood has a lot of voids. So if I take just a piece of wood that's dry and I measure the density of that piece of wood, I'm going to get something that's quite a bit less dense than water. But if I reach the fiber saturation point, then go beyond and fill all of the holes in the cells with standing water and get all the way up to 100% moisture content, then that piece of wood and the water itself is going to be heavier than water by itself. So that's why a log will sink over a long period of time. Like this, waterlogged log going to the bottom of the water. But that's a slow process, which means that, coming from the Ottawa Valley region, where the history is a long logging history, that's why that they can cut down logs in the forest and put them in the river and tie them up and send them down river to Quebec in order to sell them and export them, because it takes a long time for all of that water to get in the entire piece of wood. It has to diffuse all the way through. Here's comparing the specific gravity for a bunch of different species. So it's not constant. Obviously, like any other wood property, it varies dependent on species. So we have cedar, we have spruce, our light woods, hemlock, Douglas fir, and then those are all softwoods. And then as you get to the hardwoods, birch, oak, they get quite a bit heavier and denser. And that density has consequences for strength and also for stiffness. Okay, so just reviewing about shrinkage and fiber saturation point. This is a nice figure that comes from the Introduction to Wood Design book. You can see it showing what happens to the cell wall as the percent moisture content goes up. So as we have 0, we have no water inside the cell walls. They're as small as they can possibly be. We get more water content, more moisture content, more water going into the cell walls. The cell walls are soaking it up like a sponge. And then once we get to this point, 28% fiber saturation point, then we start getting free water within the cells instead of bound water in the cell walls. And so the shrinkage itself follows a curve where if we start from 0 and we start increasing the moisture content in the cell walls start to swell because they're getting wet, they're getting bigger like a sponge. Then the shrinkage is going to increase the relative shrinkage. This is set as shrinkage, which means relative to up here. But if we were talking about elongation instead, then it would be in the other direction. The size is going to elongate, elongate, elongate in the two perpendicular to grain directions until we reach this fiber saturation point, and at which point, since we're not putting any more water in the cell walls stay the same size and we have no change in dimension. So just like any property, fiber saturation point is different depending on species. The number that they recommend in the design standard is 28, which you can see here is a reasonably good average value given all of these different species. So that's all very well and good, and shrinkage is obviously a big effect. But, you know, what's the problem with shrinkage? Well, there are a few problems. We're going to talk about more problems with shrinkage later in the course when we talk about connections. But for now, here are some example problems that you could have. Okay, so let's say, for example, I have a concrete wall on the left. This is a timber column on the right, and I have beams. Now, when you have this X through something, when we're talking about wood, that means that's the cross section of that. So that means that this beam goes in and out of the page, in and out of the page. Okay, so there's a column on the right side here. There's a beam sitting on top. We're looking at the end of that beam, so that beam is going in and out of the page, and that's why we draw a cross through it like that. It's showing that we're looking at basically the cross section of the beam. So we have that here, and on top of the concrete wall, we have a kind of sill plate here, which is another piece of wood that we're looking at the end of. And let's say that that piece of wood is smaller than this beam, because here, this piece of wood doesn't have to take bending. So it's just a small piece that we have something to nail into, for example. But this one here, since it's a big beam, it's taking bending, it has to be deep. Pardon me. So then if we have joists on top and we have some shrinkage, so let's say that we put this beam here and this sill plate in, and we put them in at a relatively high moisture content, and then later, as the building is enclosed and everything is climate controlled, the wood starts to dry out and off-gas water. Then we know that the cross-sectional dimensions of that piece of wood are going to shrink. Not just like this, but also like this. Here we're showing just the vertical shrinkage. Okay, but you know as well that it's going to also shrink in the horizontal direction, these pieces. Okay, so if those two are different heights, we know that the percentage shrinkage of the two is going to be the same. So, you know, they might shrink 4% or something in that direction, but it's a percentage of the total dimension of that piece of wood. So if I have a small piece that shrinks 4%, that 4% is going to be smaller than if I have a big piece that also shrinks by 4% of its dimension. So that means that this piece of wood on the right is going to go down further than the piece of wood on the left when it shrinks, which means that now the joists are going to all be on an angle. And, you know, if this is a determinate structure, then that might not be a big deal in the sense that we just have to deal then with a sloped floor. But if this is a indeterminate structure, like this beam is continuous over a couple posts, then we're going to be inducing forces in the beam because of that shrinkage. You can go back to structural analysis to understand what I mean by that. So what would we do in order to solve that problem in this case, for example? Well, an obvious solution here would be to put a sill beam that's the same size as the interior beam. So even though we don't need that depth for bending, we can put that depth there so that the shrinkage is the same. So we know the shrinkage is going to be there, but to accommodate it, we'll use a different detail so that we don't induce any relative displacement. Here's another one. We'll talk about more kind of examples like this when we talk in detail about connections and how shrinkage can affect connection design. But for now, what we have here is a glulam beam, which is running in and out of plane. So what we're looking at here is the cross section of the beam. You can see, unlike for lumber where we draw a cross, if we're drawing a cross section of glulam, we tend to draw basically layers representing the glulam layers. So it's a beam going in and out of plane. And on the other side of it, sorry, so this way? No, it's the other way. Okay, so here's your glulam beam, and on the other side of it, you have a joist that is attached to the side. And that joist is connected to the beam using this steel bracket. And the intention here is that the beam sits on this steel bracket. It's got a seat. This is a steel seat here. So the beam joist sits on the bracket. The bracket transfers that load directly into the side of the glulam beam. And this bolt up here is here just to keep the joist from being unseated from the beam. So it's just kind of keeping it in place. It's not intended to take any load. It's just for safely keeping everything where it's supposed to be. Now, after this starts to dry, so let's say it went in at a high moisture content. There's a lot of reasons why it could have had a high moisture content. It could have to do with construction. So when you bring wood on site, maybe it has to sit there for a while. Maybe it rains, maybe it's under tarps, but it's not perfect, or maybe it's just really humid out, and the wood will take up moisture from the environment until it reaches its equilibrium moisture content. So let's say when it was installed, it was at a high moisture content, and that's also when they drilled the hole for this bolt, and that's when they seated everything. Now, as that piece of wood dries out, as we know, it's going to shrink. It's going to shrink in the cross-sectional dimensions. So it's not going to shrink a lot in this direction, which is the grain direction of this piece of wood, because this piece, because this piece comes out like this, right? Here's my glulam beam, and here's my piece of wood coming into the side. It's a long beam that goes this way. The direction of the piece of wood is the direction of the grain. But in the up and down direction and in the out of plane direction, which are the cross-sectional dimensions, directions of this beam, it's going to shrink. So that means this size is going to get smaller. Now what's going to happen when this size gets smaller is it's going to shrink towards whichever place it's restrained. Okay, so if there was no bolt here and it was just sitting on the bracket, then it's going to shrink downwards, right, towards the place where it's sitting. But since this bolt here restrains the movement of the beam can't move down, right? So what happens is it's going to shrink up towards the bolt, like towards the place where it's restrained. Okay, so when this thing shrinks up towards the bolt and down towards the bolt from the top, we're going to form a gap here at the bottom. And that's very bad for this connection, because this connection is intended to transmit the load in bearing directly on this seat. But what happens when there's a gap that forms here is now the load is going, instead of directly to the seat, it's going through the bolt. And when we do that in this connection, what's happening is now the bolt is taking all the load, and we're loading this joist in a direction that is tension perpendicular to grain, which is very, very bad way to load a piece of wood, as we'll learn later. So what happens is this piece of wood's going to split. Could jeopardize the integrity of this entire piece, and you might get a collapse, especially if all the connections are like this and they're all lined up in a row. Maybe the whole floor is going to be jeopardized. So how do we solve this problem? It's not so bad. Just put the bolt lower. Why is that better? Because shrinkage is a percentage of the length, right? So if we get 4% shrinkage, 4% of this height is going to be a lot less than 4% of this height. If we have it low enough, that amount of shrinkage is going to be accommodated just by the construction tolerances. So there's a hole around this bolt. So there's a little bit of movement that can be accommodated here, and the beams still sit on the bracket. But if it's way up here, we're going to have too much shrinkage for that to be compensated just by construction tolerances. So this is a much better detail than this one. Okay, to see what these look like in some kind of real, some real-ish looking situations. On the left here, we have maybe what is representing a light frame shear wall above and a light frame shear wall below, and some kind of edge beam or something like that. These steel ties here would be intended to hold together the top floor to the bottom floor. Okay, but you see here, if this was installed at a high moisture content and went to a lower moisture content, the cross section of this piece in the height is going to reduce. And in the process of reducing is going to buckle these straps. And now the straps are basically useless because they're no longer taking tension. So that means now the purpose that they were intended to serve is no longer being served. So that's a problem, obviously. On the right side, this represents what's probably a hold down bracket for a shear wall. So this is the shear wall cord here. Here's a bottom plate, and there's probably a few plates here, and then there's another wall below. And these brackets hold the whole thing together. Well, if these plates down here shrink up in the cross-section dimension, and this time in the short cross-section dimension, now they've shrunk to the point that the bolt is no longer engaged here anymore. So there's The things have shrunk, and the bolt, which used to be in contact on both the top and bottom, now has shrunk. Now has moved away because the wood has shrunk beneath it. So that does it for the qualitative description of moisture and shrinkage in wood. Following up on this, we're going to learn about how the recommendations are to deal with calculating shrinkage in wood according to the recommendations of 086.